Welcome to the Seaward Pat Refresher webinar series. This is session number 2, Basic Theory and Terminology. My name's Kevin Smith, I'm Category Manager for Test and Measurement Equipment at Seaward, and I'm going to be taking you through this webinar series. If you want to contact me or get in touch to ask any questions after the session, you can contact me through social media. I'm active on Facebook in a lot of the Pat testing forums, and you can also connect with me and obviously message me via my LinkedIn profile. So what are we going to cover today? Well, the Pat Refresher series of webinars is all about giving you a sort of start to finish view of Pat testing over the 8 sessions, over the 8 weeks that we're going to be delivering these. Last week in session 1 we looked at what is Pat testing, the legal requirements, who can do Pat testing, all those sort of introductory things. And now we're going to go on to take a look at the basic theory and terminology. It might be a bit like going back to sort of high school science lessons, but actually it is very important for those carrying out Pat testing that you do understand the basic electrical principles and electrical units that relate to Pat testing, because often people come to Pat testing without a formal electrical training background. They may be doing Pat testing as part of another job or something like that, so it's not their core role. So it is important that we get a good understanding of these units, because that's the foundations then that we can use in the later sessions. So when we're understanding things like test methodologies, pass-fail limits, all that sort of stuff, we really need a good understanding of the basics. So in this session we're going to have a look at electrical units of measurement, the factors that affect resistance, Ohm's law and the power equation, and how we refer to very large and small values. And then at the end we'll have a group Q&A session where you can actually type in your questions and I'll try and answer any questions that you've got. Now that can be relating to the subject matter, it can be general Pat or Seaward based inquiries, anything you want really. Use your chat window, type the questions in, and then I will answer those at the end. So that said, let's get started. So here we're going to start off with the basics of electrical theory. To perform Pat testing, you will need a basic understanding of electrical theory. It's part of the requirements to be considered competent. But also, it will greatly aid you in understanding day-to-day Pat activities. Often those performing Pat do not have a formal electrical background and may have taken on Pat as part of other duties. It's therefore important that we start with providing some basic electrical knowledge to help decipher the content from future sessions. So where do we start? To the right I've listed common electrical units that we come across during Pat. This is not an exhaustive list, but understanding these units will cover most situations. It's important that you do not only know the units and the quantities they relate to, but that you have a good understanding of how their properties are affected. For example, with changing cable length or cross-sectional area. So what have we got? Let's start off. First one, nice and easy, is the amp, or the ampere to give it its proper title. And this is the unit of current, electrical current. Another very common one, the volt, obviously the unit of voltage. The ohm is the unit of electrical resistance. Watt is the unit of power. And hertz is the unit of frequency. And we're going to look at each of these properties in a lot more detail in the coming slides. Okay, so the first one we're going to look at is current. Electricity is simply a flow of negatively charged particles called electrons from one place to another. Similar to the amount of water flowing in a river, the current of an electrical circuit simply tells us how many electrons are flowing past a set point each second. The unit of current is the ampere, commonly known as the amp. The greater the flow of electrons, the more amps are said to be flowing in the circuit. Often the letter I is used in equations to represent current. All electrical equipment use a flow of electrons or current to perform their intended function. For example, electrons flowing through the heating element within a kettle create heat, which is used to boil water. A common example of the amp you may be familiar with is the term 13 amp fuse. Often amps are expressed using the letter A, e.g. 13A means 13 amps. So now we'll look at voltage. Negatively charged electrons are attracted to areas of positive charge. The greater the difference between negative and positive, the greater the energy with which the electrons move. The difference between positive and negative is often described as the potential difference, and more commonly, voltage. The unit of voltage is the volt, and is used to express the potential difference between positive and negative. For example, a battery with 12 volt potential difference between its positive and negative terminals would commonly be described as a 12 volt battery. Here we're going to look at resistance. Each material has a unique atomic structure, with varying numbers of electrons positioned at varying distances from the nucleus. Therefore, the attractive force which binds the electrons to their parent atom varies greatly from material to material. Some materials, such as copper, have only a very weak hold on some of their electrons. These materials are known as good conductors. Materials which are good conductors are said to have a low resistance, as they allow electrons and therefore electric current to move easily through them. Other materials such as PVC or rubber hold tightly to their electrons and therefore would be described as good insulators. Insulators resist the flow of electrons and are therefore said to have a high resistance. The unit of resistance is the ohm, which is often expressed using the symbol omega. As electricians, we take advantage of the properties of materials, particularly conductors and insulators, to control the flow of electrons, making electricity travel where we want it to go. So here you can see we've got a picture of a normal bit of flexible cable with the cores exposed with the end stripped back. So a little bit of terminology that we need to clear up here. So the outer core or the outer layer of insulation that you will see on a cable is generally referred to as the sheath. And the purpose of the sheath is that it actually provides mechanical strength of the cable, and it also provides protection to the cores inside. So the outer sheath there is really for its mechanical strength and to actually protect what goes inside and stops that getting sliced or abraded or worn away. Then inside that we've got the actual insulation itself. So this is what's there to stop the electricity coming out of the conductors and actually separate us from the live parts inside. And the insulation is actually usually in cables coloured so that we can actually identify the purpose of those conductors at both ends of the cable. Now, inside that we have the conductors, and the conductors are generally copper in most cases. You can get other cables, but generally most of the conductors we deal with are copper. And because this is a flexible cable, this is the type of cable that we'd use on an appliance, they're made up of many tiny little strands. Sometimes you'll see solid conductors, but generally they're not flexible. They're designed for fixed wiring. So the normal, maybe you've heard of twin and earth cable. Twin and earth cable has fixed, it's meant for fixed wiring, so it has solid conductors in there. They're not made to bend. Whereas flexible cables obviously made to bend, so we make it up of a lot of little strands, which makes it easier for that cable to bend. Now, the terminology, the actual the wires in here have different names based on the purpose of them. So the brown wire, sometimes people would call this the live. And that's old terminology. That's sort of pre-90s terminology, is to call the brown wire the live. Sometimes you will hear it called the phase as well. But actually the correct terminology nowadays, and has been for about the last 10 years, is to call it the line, L-I-N-E conductor. So it's the line is the brown one, L-I-N-E. That's the current terminology. Like I say, people will use the term live, but that's old terminology when it's used in relation to the brown cable. Then we have the blue wire, which is the neutral. That's generally what most people would call it. And then we've got the yellow and green there, which is the earth, or the protective earth, or sometimes referred to as the ground. So that's the protective conductor, and that's generally used in Class 1 equipment as the protective conductor. We do have Class 2 equipment, and we'll get onto this in future sessions, where it only has two wires in there, the line and the neutral. So there might not be an earth in all of the cables, but where we've got a 3-core cable, generally we'll be looking at a brown line, a blue neutral, and the yellow and green cable is the earth. Now, I did mention the term live, and what we actually have nowadays is that both line and neutral are generically referred to as live conductors, because they are actually carrying live current. They're designed to be live. So in that case, we don't just use the term live for the brown wire. The line and the neutral are both considered to be live conductors. They're both current carrying conductors. So from that side of things, they're referred to as live conductors. So when you hear in later sessions, you might hear us talk about we test between live parts and earth. Then when we're talking about live parts, again, the line and the neutral are included in that when we talk about live conductors or live parts. So just be aware of that terminology, because there's a lot of misunderstanding around there and what these things are called. But that should give you a good breakdown of how these things are set up. So flexible cables are often classified by the size of their conductors, usually expressed in the cross-sectional area in millimeters squared. This number relates to the cross-sectional area of each of the conductors. For example, a 0.75 millimeter squared 3-core cable will have 3 conductors, each having a cross-sectional area of 0.75 millimeters squared. So it's not the combined area of all 3, it's each core will be a 0.75 millimeter squared cable. And generally with flexible cables, they will all be the same size. Twin and earth cables that are used in the fixed wiring, sometimes you'll have a different size for the live conductors than you will for the protective conductor. But generally in flex, they're all the same. They're going to be 2 or 3 cores of the same size. The cross-sectional area of the cable can be easily identified, as it's usually printed onto the sheath at regular intervals along its length at the time of manufacture. And you can see a couple of examples that we've put in the presentation here. So the top one there, you can see it says 3G, which means it's a 3-core cable. 3G means 3 core, so we'd expect to see in there a line, a neutral and an earth. And it says it's 1.0 millimeters squared. So it's 3 cores, and each core is 1 millimeter squared in cross-sectional area. Again, the next one down is a 2-core cable this time. You'll see it says 2 times. So it's 2 times 0.75 millimeter squared. So it's telling us that in that cable there's 2 0.75 millimeter squared conductors. And obviously in both cases, each of those conductors will be made up of many smaller strands of wire. But those smaller strands of wire, when added together, have the overall cross-sectional area of what's displayed on the cable. So, what factors affect the resistance of a conductor? So the resistance of a conductor is dependent on 4 properties. And you can remember these properties by using the acronym MALT, M-A-L-T, MALT. It's the nice easy way of remembering. So the first one, the M that we're going to look at, M stands for material. As I mentioned earlier, each material has a different atomic structure. Therefore, each material will have a different resistance. This property is known as its resistivity. So each material, whether that's copper, silver, whatever it is, anything on the atomic, the periodic table, anything there, will have a set resistivity. That's a fixed property based on the atomic structure, how those electrons are arranged within that material. Usually this property has limited effect during pat testing, as most conductors are made of standard materials such as copper, and these materials are unlikely to change during the life of an appliance. So would there be a difference between a copper conductor and a gold conductor? Yes, there would. The gold would conduct better than copper. But from a pat testing point of view, generally the materials we're going to come across, it'll be a copper cable, and that's not going to change. So when you're pat testing between, from one year to the next, you're not going to see any changes due to the change of material, because, a copper cable is not going to turn into gold. Wish it did, but not going to happen. So the material, although material is part of molten affects the actual properties of a conductor, it's very much fixed. We pick copper for a reason, because it's a very good conductor, and that's it. It's not going to change. So from a pat point of view, yes, it's good to know what that material is. And sometimes when you've got substandard or counterfeit products, you will actually see that it's a very poor quality copper, and it may have other materials mixed in with it, and that overall again affects the resistance, affects the resistivity. So you can see poor quality copper leads that have got very impure copper in there actually having a lot higher resistance, and that's due to the material, due to the structure of the material. So again, it can affect it, but it's not going to change over time. So again, the next property we're going to look at here, the A in mult, is for area, or in our case, cross-sectional area, the area of the cross-section of the conductor. So the cross-sectional area of a conductor, when increased, so when we make the cable fatter, for want of a better term, allows electrons to flow more easily through it. Think of a big pipe, we make it bigger, more of those electrons can flow through. This has the effect of lowering the conductor's resistance. So if it's easier for electrons to flow, that's lower resistance. The opposite effect can be observed when a conductor's cross-sectional area is reduced, thus increasing the resistance. The cross-sectional area of a conductor is therefore said to be inversely proportional to its resistance. So if the cross-sectional area goes up, the resistance comes down. If the cross-sectional area goes down, we make it thinner, the resistance goes up. So just simple examples there, if we've got a fatter cable, we would expect a lower resistance if we measured it than if we got a very thin cable. So we can see this when we do pat testing. So it's a direct relationship between resistance and cross-sectional area. So if the cross-sectional area of a conductor is doubled, its resistance actually halves. And if we halve the cross-sectional area, the resistance will actually double. So it's a very direct relationship between these values. Understanding the relationship between cross-sectional area and resistance can be useful. A typical example being, you have a 0.75mm squared cable with a measured resistance of 0.5 ohms, half an ohm. If this cable were to be changed for a 1.5mm squared cable, what would the effect be on the measured resistance? So the answer to that question, if we double the cross-sectional area, so we've gone from 0.75mm squared to 1.5mm squared, so we've changed the cable, maybe on a piece of equipment, cable got damaged, we've changed the cable for one that's actually got twice the cross-sectional area, it's twice as fat. And what effect would that have? Well, the resistance, we'd expect to see the resistance halve. So if we tested it last year, and we'd got 0.75 cable on there, and we got half an ohm, this time we've actually changed the cable, and it's now 1.5, we'd expect to see half the reading. So if we saw the same reading, that would actually give us an indication that maybe there's a bad connection somewhere or something like that. So we can interpret this as part of our testing to actually understand, the results that we're getting and whether they're good or bad. So the next property in mult is L for length. The length of a conductor is often a key factor that must be considered when portable appliance testing, specifically in relation to testing long extension leads. If we increase the length of a conductor, we increase its resistance. And if we shorten a conductor, its resistance will decrease. Therefore, the length of a conductor and its resistance are said to be directly proportional. So, if the length goes up, the resistance goes up, length comes down, resistance goes down. If the length of a conductor doubles, then its resistance also doubles. It's a fixed relationship. If the length of a conductor is halved, then the resistance will halve. So you can see this causes us problems when we've got things like long extension leads, because if we've got an extension lead that's 10 times as long as a normal lead, then the resistance is also going to be 10 times that value. So that's why long extension leads and things can cause problems, because of the high resistance of the protective conductors. And we also need to correct our pass-fail limits and things like that for it, because we can't use the same pass-fail limit on something that's got a 1 metre lead as something that's got a 10 metre lead, because obviously the resistance values are going to be 10 times more. And that's okay, that's the laws of physics. But if we're using the same pass-fail limit for a 1 metre lead as we are for a 10 metre lead, the 10 metre lead's going to fail. Not because it's actually faulty, but because we're applying the wrong limits. And that's a very common mistake that gets made time and time again with pat testing, and we'll talk about that in future sessions. So, length. This property is also useful for real-life calculations. A typical example being you have a 10 metre extension lead with a measured conductor resistance of 1 ohm. So we've got a 10 metre lead and it's got a 1 ohm resistance. If the length of the lead is reduced to 5 metres, what will the new measured resistance be? So remember, we said if you halve the length, you halve the resistance. So we've gone from 10 metres to 5 metres. In this case, halving the cable length will halve the resistance, so the correct answer would be 0.5 ohms. Now generally, 1 ohm is probably quite high for a 10 metre lead, and we go off the resistance, but we just pick these figures because they're nice and easy for you to see the relationship. But the principle is, we halve the length of the lead, we're halving the expected resistance. We double the length of the lead, we're doubling the expected resistance. So again, it's having that understanding. This is why this session is very, very important, because if you understand these properties and you understand how they relate, that gives you a very good idea for actually how all this lot fits together and how you can interpret your own testing and your own test limits and results. Now, the final part of mult, M-A-L-T, mult, is temperature. So the temperature of a conductor also affects its resistance. If we increase the temperature of a conductor, so the cable gets hotter, we also increase its resistance. If we lower the temperature of a conductor, we'll decrease the resistance. So hot cables have higher resistance, colder cables have a lower resistance. So while changes in temperature do affect conductors' resistance, temperature is not a property often taken into account during portable appliance testing. And the reason for that really is that actually, although it does affect it, it's not a huge effect. And generally the cables that we're dealing with, as it says here, pat testing usually assumes to have taken place at normal ambient temperature. So generally when we're testing a piece of equipment, we're assuming that it's at normal ambient or room temperature of 20 degrees. So any small changes in temperature above or below 20 degrees are not really significant enough to affect the results. So although, yes, if we were testing at 21 degrees, we could correct it. But I think the factor for copper is sort of 0.005 ohms per degree C. So it is a tiny little change in your readings per degree C. So if we were looking for high levels of accuracy, really high levels of accuracy, We could correct for temperature if we wanted to when we do pat testing. And if we're dealing with very hot or very cold cables, if you're pat testing and it's almost freezing, or the leads are really, really hot, potentially you could see problems. You could see changes in there. But normally with pat testing, certainly within the remit of the IET code of practice, they generally just assume an ambient temperature of 20 degrees C. The resistance values, the pass-fail limits and everything allow for a pass-fail, a resistance value of 20 degrees C and all the pass-fail limits in the tables. So we just assume testing has taken place at 20 degrees C, and it doesn't generally vary much either side of that. But temperature does affect the resistance of a conductor. The hotter the cable, the higher the resistance. The cooler the cable, the lower the resistance. But it's not like the same effect as you would have with cross-sectional area or with length, where actually doubling it has a doubling effect and things like that. These are small variations or smaller variations in resistance for changes in temperature. So the next bit we're going to look at here is Ohm's law. Now Ohm's law is very useful because Ohm's law is the equation that defines the relationship between current, voltage and resistance. We looked at these three properties earlier, and this is now the three of them coming together. What's the relationship between these three things? So when given any two of these three properties, we can use Ohm's law to calculate the third. So for example, if we know the voltage and the current but we don't know the resistance, we can work that out. So Ohm's law can be expressed in the form of a triangle. So on the right hand side here you've got the Ohm's law triangle, and this is really a good way to actually work out the equations, but it's also a very good memory aid. So you'll see I've laid out the triangle here, and we've got VIR, voltage, current and resistance, and we've also got the units, the volts, amps, ohms on there. So we can use the triangle to remember the three Ohm's law equations. You simply cover up the property you are trying to find with your finger, then the relationship of the other two properties gives you the other half of the equation. For example, if we're trying to find voltage and already know the current and the resistance, we can simply place a finger on the V. So if you do that, you place your finger over, you cover over the V, and what you're left with is IR, or I times R. So that part of the Ohm's law equation, V equals I times R. So the voltage is always equal to the current multiplied by the resistance. Now if we wanted to do that for the other equations, you can see the three equations we've got around the outside of the triangle there. So resistance equals voltage divided by current. So if I put my hand over the R for resistance, I've got V over I. So it's voltage divided by current. And if I want the current, then again, cover up the I equals V over R. So again, really easy. If you can remember the triangle, that then allows you to change between any of these values. If you've got two of them, you can work out what the third one is in any electrical circuit. So again, it just helps you to convert these things round. You've got a specific resistance, you know what the voltage is, what's the current likely to be. So you can use Ohm's law to actually work out these. And Ohm's law is sort of, used as the basis for many electrical equations. One of those equations is the power equation. So power is something we haven't talked about yet, and power is quite common when we're talking about pat testing. We use the term watts quite often. Sometimes you'll see kVA, kilovolt amps, and things like that. For power. So power is the combination of voltage and current. So again, when you're looking at this, power is really the ability to do work. So if we've got a lot of voltage but we've got no current flowing, we can't really get a lot done. We've got loads of energy but we've got no current flow. So again, there's not a lot going to happen. Similarly, we could have a lot of current, but not a lot of voltage. So there's not a lot going on there. There's not a lot of oomph. There's not a lot of power. So power, really, the oomph, the sort of ability to do work, comes from the combination of voltage and current together. And that's really where, we actually get an idea of the oomph, the ability to do work that a piece of equipment has got. So the unit of power that we generally talk about is the watt. We use the letter W for that. And everybody's familiar with terms like a 100-watt light bulb or a 10-kilowatt shower. And generally we're talking about, the ability those things have to do work. So if we've got a 40-watt light bulb and a 100-watt light bulb, there's more power, there's more ability to do work, there's more light, more heat coming from a 100-watt light bulb than there is from a 40-watt light bulb. Same with a 10-kilowatt shower. If we've got a 6-kilowatt shower, we haven't got as much heat, we haven't got as much energy coming off a 6-kilowatt shower as we would with a 10-kilowatt shower, so we can't heat that water as quickly or heat as much water for the shower. So again, power is where we've got the voltage and the current coming together to actually give us the ability to do work. So power can be calculated from a similar equation to the Ohm's Law equation. Here you can see that given the voltage and the current, we can calculate the power. So P equals V times I. The power is the voltage multiplied by the current. So again, just like with Ohm's Law, we can actually put this into the form of a triangle with power at the top, voltage and current. And again, to transpose that, if we've got the voltage, so we want to know the voltage and we've got the power and the current, we put our hands over the V and that gives us P over I. Or if we've got the current, so we want to work out the current and we've got the power and the voltage, again we can do similarly, put your hand over the current and it says P over V. So again, we can derive all of these equations and transpose all of these equations using simple power triangle. Now the power conversion is quite useful because sometimes what you may come across is that you might have an appliance where you know the power, it's a 600-watt appliance, but you don't know what the current is. So you think, well, I know it's 230 volts, and I know it's, say, 600 watts, but how do I know what the current is? How do I know the fuse is right, or the rating of the cable is right, or that sort of things? Well, you can use these equations then to actually work that out and actually work backwards. Similarly, if you knew, well, I know what current it's drawing, and I know it's 230 volts, but how much power is that? How does that equate to, So again, we can use these equations as part of what we're doing with pat testing, with looking at equipment to actually decide whether things are actually aligning with what the equations say they should, or to be able to determine values that we don't know. So the next one we're going to look at is frequency. Most people have heard of the two types of electric current, DC, direct current, and AC, alternating current. A typical example of DC is a simple 12-volt battery. In a battery, the positive terminal always remains positively charged, and the negative terminal remains negatively charged. So the electrons always flow in one direction around the circuit. Therefore, the battery's output is said to be a constant 12 volts DC. Alternating current is most commonly found in the mains distribution network. The main socket outlet in your home provides a nominal voltage of 230 volts AC. Alternating current, as the name suggests, does not have a constant polarity. The flow of electrons first flows in one direction, then in the other. Our 230 volts mains voltage actually changes direction 50 times per second. This is known as its frequency, which we state as 50 Hertz. So frequency, the unit of frequency is Hertz, and as we say, the mains changes times 50 times per second, so that would be 50 Hertz. So DC basically has a frequency of 0 because it doesn't change. it just stays constant polarity. So DC has a zero frequency, or DC frequency, because it doesn't change polarity, whereas alternating current, the speed at which it changes, how many times it changes per second, is what we refer to as the frequency. And as we say in the UK, the mains frequency is 50 Hertz. In this final section, we're just going to have a look at how we deal with large and small numbers. We're all familiar with how large and small numbers are used in everyday life, although we might not notice them. Typical examples include kilograms, so that's thousands of grams, millimeters, that's thousandths of meters, megahertz, that's millions of hertz, and gigabytes, that's actually billions of bytes. So these sort of prefixes that we put on words, kilo, milli, mega, giga, are used to determine very big or very small numbers. And they become quite common to the point where we don't really notice them. But they are used a lot within electrical properties, and particularly when we're doing pat testing. So one of the strengths of metric systems of measurement is that metric units can be easily expressed in multiples and submultiples, which allow us to easily convert values into more meaningful numbers, giving us greater understanding and the ability to avoid the errors associated with long numbers containing lots of zeros. So all the metric units described earlier can be expressed using multiples and submultiples. Below is a table showing the typical range of values encountered during portable appliance testing. Okay, so what we get on here, the common ones that we're likely to come across is obviously mega, and mega is a million of something. So when we talk about mega, we're talking about a million of something. So typical example that we come across is when we're measuring insulation resistance. Remember, we were saying that the resistance of insulation should be very high because it's a good insulator, it stops those electrons flowing. So when we talk about insulation resistance, we're not talking about small, low resistances in ohms. We're actually talking in mega ohms, millions of ohms. So you'll notice that we use the capital letter M in front of the ohm symbol, the omega symbol, to denote that we're talking about mega ohms, millions of ohms. Kilo means 1,000 of something. So if we've got 1,000 of something, we'll say it's a kilo. In this case, typical example, we talked about it earlier with showers and things like that, is a kilowatt, 1,000 watts. So when we're actually recording that down, we'll use the letter K, it's a lowercase k, and the lowercase k denotes that it's kilo. So whatever we've got there, it's times by 1,000. So if it's 1 kilowatt, it actually could be written as 1,000 watts. Units, a lot of things we deal with are just in base units, and whenever we do calculations, we always need to convert these things to base units. Because if we try calculating and we start dividing millions by thousands by units, it all goes very wrong. We get too many zeros and it all comes unstuck. So generally when we're doing calculations, we convert back into the base units. But things like amps quite often are just in base units, volts particularly, ohms, and again we can use watts and hertz and things like that. But sometimes we may have to convert these, as we said with something like mega ohms, convert it into ohms by timesing it by 1,000,000 effectively, to get that into a format we can actually calculate. Now they're the very big units, mega, millions, thousands. What about the small units? Now generally with pat testing, the smallest we tend to go is milli. Milli, we use the letter a lowercase m for milli to differentiate it between mega as an uppercase M. It's a big unit, so we have a big letter, whereas milli is a small unit. Now milli is going the other way. This is talking about thousandths. So this is taking something. So a millimeter, you might be familiar with, is actually 1,000th of a meter. So when we're talking about ohms, quite often with resistance, we can be talking about quite small values, particularly if we're talking about the resistance of conductors. So we can be talking in milliohms, thousandths of an ohm. So you will see that, and certainly with amps again as well, if we're actually talking about very small levels of current, which is quite common, we'll use the lowercase m, milliamps, and they're thousandths of an amp. So just be aware of how we use these values, and we do use them quite interchangeably through the rest of the topics, and you'll see, like I say, when we talk about insulation resistance, we'll be talking in mega ohms, and then we'll be talking of milliamps, and we might be talking milliohms, and things like that, kilowatts, and it all can get a little bit confusing. So it's important to include this and just get this bit of understanding there. It's stuff we're all familiar with. We're familiar with meters, millimeters, kilograms, all these sort of things that we come across with metric units. But it's just getting that understanding when we're talking about pat testing, and understanding that if we're talking about conductor resistance, we might be talking in milliohms, but then because conductors should have very low resistance, but when we're talking about insulation resistance, we could be talking in mega ohms, millions of ohms. So it's, although it might be 1 milliohm or 1 mega ohm, you think, well, isn't that the same? The only difference is a lowercase m or an uppercase m, but actually there's a billion times difference between the two. 1 milliohm and 1 mega ohm are a billion times apart. So it can make a huge difference. So just important that you understand the differences of these, and actually it just helps with the understanding of the things that we'll be talking about later in this series. So in conclusion, session 2, basic theory and terminology. We've looked at the electrical units of measurement associated with pat testing. We've looked at the factors that affect resistance, molt. We've looked at Ohm's law, the Ohm's Law Triangle, the power equation and the power equation triangle, and we've looked at how we refer to very large and very small values. So hopefully you'll agree that's given you a good grounding in understanding all of those values that we can then take on to later sessions and actually use those values with confidence then. So next session is actually session 3, and session 3 covers the types of equipment and their construction. So we're going to look at what types of equipment do we test, how are they differentiated, what's the differences, what do we need to be aware of, but also equipment construction. And equipment construction is really important. We'll look at things like the equipment construction classes, class 1, class 2. How do we work out what's class 1, what's class 2? So that's quite an important session coming up there, session 3. But we'll take the knowledge that we've gained in the previous 2 sessions now and really utilise that in session 3. So now it's time for your questions. So I'm happy to take your questions. So if you can type those into the chat box, and we'll go through and I'll answer your questions now. Thank you very much for your time.